Hello again. In this video, we're going to go over 3 theorems that are in this section. The first theorem that we're going to go over is called the characterization of linear dependent sets. And it says an index set S consisting of 2 or more vectors is linearly dependent if and only if at least one of the vectors in S is a linear combination of the others. This theorem does not say that every vector in a linear dependent set is a linear combination of the preceding vectors. It says that there is at least one of the vectors, not all of them, is a linear combination of the others. And the proof is very similar to the proof I did in the last video, where a set of 2 vectors is linear dependent if at least one of the vectors is a multiple of the other. So the proof goes something like this. If for some Vj in S equal to a linear combination of other vectors, then Vj can be subtracted from both sides of the equation, producing a linear dependence relationship with a non-zero weight -1 on Vj. For instance, it gives this equation just with 3, and it shows that you can bring that over there, and then you would have, thus S is dependent. You would have it, and thus S is dependent. The next paragraph goes over the conversely, the other way. Because if you remember, this is an if and only if. So I'm going to use this notation like I did in the last video when I proved an if and only if. So this way, this first paragraph was really Q implies P because we assumed that there was at least one vector in S that was a linear combination of the others, and here it was. And then we showed that it was linearly dependent. So the second paragraph is going to go the other way around. P implies Q. So we're going to suppose S is linearly dependent. And then we want to show there is at least one vector in S which is a linear combination of the others. So if V1 is 0, then it is a trivial linear combination of the other vectors in S. So otherwise it is not 0. And there exist weights C1 through Cp, not all 0, such that this happens. Why? Because it is linearly dependent. Let J be the largest subscript for which Cj does not equal 0. If j equals 1, then you would have this, which is impossible because V1 is not 0. So j better be bigger than 1, and you would have these extra guys here. Why? Because if you remember, j was the largest subscript where it was not equal to 0. So all these are not 0, but these are. So we just add them until you get to Vp. And then we can solve for our largest guy, our Cj, Vj. Solve for this term right here. And by bringing everything else over, dividing by Cj, you found a vector, one vector, that is a linear combination of the other. So let's look at an example of this. Let U be this vector 3, 1, 0, and V be 1, 6, 0. We're going to first describe the set spanned by U and V. The span of U comma V is going to be the xy plane. Why? Because there is a 0 here, and so Z is always 0. And you can see this because suppose B is any arbitrary vector, we'll call it xyz, and B being the span of UV, we know B is a linear combination of those 2 vectors, U and V. And if we solve this, we can write the augmented matrix with the columns as the vectors U and V, and B we know is xyz. And you can see here that the last row, for it to be consistent, Z must be 0. And to find that it's the xy plane, nothing else is constricted, we can go ahead and reduce this to echelon form. So I'm going to switch row 1 and row 2, multiply the first row by -3, add it to the second, and I can stop here because I can see Everything else has a pivot. X and Y can be anything. So Z is always 0. And when Z is always 0, that means that what's left is the XY plane. Z is the only constriction. So that's why the span of U, V is the XY plane. Now we're going to explain why a vector W is in the span of U, V if and only if U, V, and W is linearly independent. If we explain this by a picture, you can see here U and V is in just the XY plane, right? The X3 plane, because we're going to let X1 be X, X2 be Y, and X3 be Z. So when W is in the span of U, V, it's also in the XY plane. We just proved that. And since all three of these now are in the XY plane, we can take any point on W we can find by adding some multiple of U to some multiple of V. If W was not in the span of U and V, say it was out here where the Z was not 0, then there is no way that we can find some multiple of U added to some multiple of V to get to a point on W. So W, U, and V would be linearly independent instead of dependent, which is up here. Example 4 generalizes to any set U, V, W in R3 with U and V needs to be independent, by the way. The set U, V, W will be linearly dependent if and only if W is in the plane spanned by U and V. To show this, I'm going to let W be in the plane spanned by U and V. So by definition of W being in the span of U and V, we know W is a linear combination of U and V. And by Theorem 7, we have that U, V, W is dependent. Going back and looking at Theorem 7, the characterization theorem that we just saw at the beginning of this video, it says exactly that. If one vector is a linear combination of the others, then the whole set is linearly dependent. So now let's do the converse. Suppose U, V, and W are linearly dependent. So again, by Theorem 7, there is some vector in U, V, W, which is a linear combination of the preceding vectors. And that vector must be W, since U and V are linearly independent. If you remember, when U and V are linearly independent, two vectors, one of them is not a multiple of the other. And finally, if W is a linear combination of U and V, then it must be in the span, which is what we're trying to prove. Theorem 8. If a set contains more vectors than there are entries in each vector, then the set is automatically linearly dependent. That is, if any set V1 through Vp is in Rn, is linearly dependent if the P is bigger than the N. I call it the wide theorem. And you can see that in the picture here. So if the P is larger than the N, your matrix looks wide. And if it is wide, then it's going to be dependent. Here's the proof. So we're going to let P be bigger than N, and A be the vector A1 through AP. And A is N by P. It's N rows, P columns, just by the construction of it. And the equation AX equals 0 corresponds to the system of n equations and P unknowns. If P is bigger than N, then there are more variables in the equation. So there must be a free variable. It's consistent because AX equals 0 has a trivial solution. AX equals 0 is always consistent. So therefore, the columns of A are linearly dependent. To see example of this, let's look at example 5. The vectors 2, 1, 4, -1, and -2, 2, all in R2, are linearly dependent by Theorem 8. Again, they're in R2, and there's 3 vectors. So the number of vectors, 3, is larger than 2. And it looks wide, as you can see. Because there are 3 vectors in the set, and there's only 2 entries in each vector. Notice, however, that none of the vectors are a multiple of the other. But it is still dependent. There's a picture. These are dependent because we're in R2. And you can see this using matrices as well. Ax equals 0 must have the trivial solution. And if I switch the rows, multiply the first row by -2 and add it to the second, here are your pivots. You can see there's a free variable. Whenever there's a free variable, there's many solutions, not just the trivial solution, hence dependent. Our last theorem tests the dependence of a set that has a 0 vector. So before we look at the last theorem, let's look at this example. Is the 2 vectors in R3, being 1, 2, 3, and 0, 0, 0, linearly independent? The answer is no, since if you write a linear combination of C1 and some C2 with the first vector and the second vector equals 0, this has more than the trivial solution. I get that C1 is always 0 because the second term, 0 times C2, is 0. But C2 can be anything. C2 can be any constant. So there is a non-trivial solution. So we know that these 2 vectors are dependent. You can see this also with this augmented matrix here. And if you reduce this by getting a 0 where the 2 is, multiplying the first row by -2, adding to the second, doing the same thing to the third row, multiplying by -3 times the first row, adding to the third, you would get this matrix. And so you can see C1 is 0, but C2 is free. If a set of vectors in Rn contain the 0 vector, then the set is linearly dependent. It's that simple. And here's the proof. By renumbering the vectors, we may suppose V1 is 0, one of them is 0. Then the equation 1 times V1 plus 0 times V2 all the way to 0 VP equals 0 has more than the trivial solution. We just saw it right there. There's the C1. C1 is 1. There is some constants that make this 0, which shows by definition that S is linearly dependent. So example 6, we now can determine by inspection if a given set is linearly dependent. So part A is dependent because of the wide theorem. There's more vectors than entries. Part B is dependent because we have a 0 vector from Theorem 9. Part C seems like it's dependent because we have 2 vectors where it looks like one vector is a multiple of the other, but it all fails in this last entry here. Because if you take V1 times -3/2, it looks like you get V2. -2 times -3/2 works is 3. 4 times -3/2 is -6. 6 times -3/2 is definitely -9. But 10 times -3/2 is not 15. -3/2 times 10 is -15, not 15. So these 2 vectors are independent. Independent since neither vector is a multiple of the other. We saw that in the last video.